All right, so let's start with the class now. Um, so I guess we were basically talking about, so far we have been talking about 1D arrays and what kinds of decisions and sub problems arise when you are typically given 1D arrays in questions. So did you guys have a chance to solve the combination sum question? If you remember, we gave that as a homework, a combination sum with duplicates. So if you remember, this question was basically that you have an array of numbers, and what you had to do was you had to, there could be duplicates in the array. What you had to do was you had to find all combinations within the array which sum up to a particular target. And we looked at how to do this question with both the decisions. One type of decision was include exclude, so we coded this in the class. And then another type of decision was like all possibilities with which the subset can begin. So like it can begin with 2 or the minimum, let's say the minimum element in the subset. This was the decision, and for this I had given you a homework to try it on your own, and this we had done in the class. So did you people get a chance to try this? Like, did anyone successfully do it? What is the problem with the original approach? Like, nobody tried it? Shall we discuss it in the class or shall we move on? What do you guys want? What about others? All right. Okay, let's move on. So today, let's look at 2D arrays and what kinds of problems typically you encounter when you are given 2D arrays and matrices, and what kinds of decisions can emerge as a result. So to begin with, let's go ahead with this question. So is this link visible to everyone? I guess after the Zoom update, it might not be so explicitly visible to everyone. Yeah, okay. So just go through it. This is one of the Google questions that, like, there was a time when this was one of the favorite questions of Google. They've stopped asking now, but it used to be one of the primary questions like Google used to ask in one of the earlier rounds of interviews. So let's see this question. So just acknowledge once you have read it. Let me also read it.
So
Yeah.
So you said this was once the favorite question of like in Google interviews. So do companies repeat their questions for various applicants, or like similar logic was used in multiple questions?
No, so questions are repeated. It's not that questions cannot be repeated. So when I say like what are you talking about, campus placements?
No, sir, off campus. When
Off
somebody applies.
campus, yeah, off campus, I guess it's, so typically I'll tell you what happens internally. Might not be applicable to Google, but is applicable to a wide variety of companies, including Oracle. So what they do is every year when they like they have a set of questions that they prepare, and that serves as a reference for any person who is taking an interview. So they typically pick up questions from there, and that reference material is prepared like by the people who know algorithms and data structures to a good amount of, to a good extent. So if like during like that phase or that period this question was there in their seat, and so it just used to happen that interviewers used to ask this question a lot. So questions are repeated. There is no,
Okay, sir.
there's nothing like questions can't be repeated. So what is any ideas around how to do this? What kind of decision can we make here?
So will we have like 4 directions as per
Okay.
decision?
So what is the sub problem then?
I'll have to think.
Yeah.
Sir, here, excuse me, sir.
Yeah.
Sir, here same letter can be used more than once in the question.
What do you mean the same letter can be used more than once? Same letter of the matrix
So in
or
the
of
question
the word?
it is of the cell.
Of the cell. So when you are looking at for a
It
particular,
is written may not be used.
may not be used more than once. Yeah, I mean it's basically, yeah, Drishan, you're right. So basically, for a particular alpha, so one index can be used only once. Let's just put it that way. So if you take index ij in your solution, then you cannot use ij again for another character in the of the same word. Yeah, what is the decision, Aryan? We will have 4 directions, 4 choices. Okay. We try 8 directions from that cell for a match. Yes, that's true.
So the decision would be we'll check the first letter, the position of the letter in the word we are searching for. According to that, we check the direction. The first decision would be we check the whether the direction of the next. If you're moving right, whether the right letter is the next letter in the word.
Okay.
So if it is true, then we call the function again from that point, or else we just stop that call, recursive call from there.
Okay. So what is the sub problem then?
So it will be checking the 4 directions for that next letter, right? That should be the subproblem.
Yes. So
No, not 4. Actually, you would not consider the
parent. So you will have
Yeah.
3. That's okay. But what I mean to say is, what is your sub problem? Sub problems in the sense that when you are reducing down a problem, right?
So you'll go ahead in the word that you're supposed to check for. Like you'll advance to the next letter.
Yeah. So what is it? Is it a prefix array, suffix array? What is it basically that you are left with?
Suffix
Once you've made that call.
So, but this is a 2D array, right? Like
Yeah. So what is it basically? it's not just a suffix array. It's a subsequence of the matrix and a suffix array of the word. So let's see. So if you see, I'll just repeat the question for the benefit of everyone. So you are given a matrix and a 2D matrix. Let's just say some word. Let's say C, A, C, D, E, F, C again. Let's say A, B, D, E. And you are given a word. So what you have to find is you have to find whether this word exists in this array or not. And typically there are certain rules. So the word should be contiguous in the sense that every alphabet of that particular word in this matrix should be either to the left from its previous. It should either be to the left or to the right or to the right, top or to the bottom. Like for instance, this is true because CAAC is present in this and the typical property is that if you take any character from the word in the matrix, it is basically separated from its previous word by either like it is either present to the right of it, immediate right, or to the immediate bottom, or to the immediate top, or to the immediate left of it. So for instance, this is also one valid match. So this is basically, so if you take A here, it is present to the immediate top of its predecessor. If you take this A, it is present to the immediate right of its predecessor. If you take this C, it is present to the immediate right of this predecessor. Correct? So that's basically the constraint that is given in the question. So how do I, so what goes on in my head when I look at this type of a problem? This is the word search problem. So first things first, I know that there can only be certain indices in the matrix from where I can start. Correct? Because I have CAAC, I know that cells which do not have C, I cannot start from there. Right? So let's say this is B, D, E, F, G, C, C, B, E. So I know that when I'm starting, I definitely cannot start with this cell or 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 this cell. This, I cannot start. I can only start from cells which have C. Correct? So that's basically my first observation when I see this question, that I can only start from what are the possibilities from where I can start. There are only limited possibilities, which are, for finding out these possibilities, I will have to go through the entire 2D array and find those cells for which begin with a C. Only those for those cells I can start the searching. That's basically the first part. So first part of this algorithm, I tell myself, okay, let me find the starting position in the 2D array. There is like no rocket science in this. These are the possibilities for the starting point. Correct? Now what the next step is, okay, now once that I know a starting position or a position from where I can start the search, let me now search for the particular word starting at that particular index. Okay, so now for every such starting point, what I want to do, I want to search for the word in the matrix. So this is the second part that I want to do. And this is where recursion will come into the picture. So this part is clear to everyone. I just saw the question and I said that, okay, I will have to do it in 2 phases. Let me just find the possible starting points in the 2D array from where I can start the search. And then for every such starting point, let me try the search. So now let's move on to the core algorithm, which is given that you are starting from a particular location, how do you go about searching this word in this matrix? So let's zoom or double click on 2. So for double clicking on 2, I first have to like think about a decision. So what I tell myself is that the decision is very simple. It is basically given in the question itself that when I start from any given cell, I can either go to the right or to the bottom or to the left or to the top. I cannot go anywhere else as per the constraints of the search. So the decision is very simple. I know that I can only go to the right or left or bottom or top. So now let's talk about the sub problem. So this is the first part of the recurrent of the like the steps to compute a recursive solution. We thought about a decision, and the decision here is very trivial. Generally in matrix problems, decisions will not be very hard because they will be imposed, like the constraints will be given in the question itself. So I know that the decision is that once I know the starting point, from the starting point I can only go in these 4 directions. So let me explore all the 4 directions. These are the possibilities. So let me search in all the 4 directions, and that's the decision that I make at this particular point. So now let's see. Now let's talk about the sub problem. So how do you compute the sub problem? You take that decision and then you see that what you are left with, correct? And that's how you arrive at the sub problem. So let's think about this. Let's say you take this decision of going to the right. What is the sub problem you are left with? Now you are here. What is the sub problem you are left with? You are left with finding this half of the word, this remaining part of the word in this entire matrix, but yours in this entire matrix, but you cannot choose C again.
Suffix, right?
For this word, it's a suffix array.
We can use Boolean matrix.
Yes, I'll come to that. Clear? Is the sub problem clear to everyone? What is the sub problem? The sub problem is that first of all, how do you arrive at the sub problem? Once you make the decision, you take the decision, you go, like you follow it, and then you see what you are left with in order to arrive at the actual answer. So what are you left with? You are left with finding AAC in this entire matrix other than C. You cannot visit C again, but you have to find the remaining AAC in this matrix. And obviously you have the that's the problem now, correct? So what are you left with? Basically you are left with a suffix array and a subsequence, suffix array of the word and a subsequence of the 2D matrix, correct? How this part I guess everyone gets. Can anyone tell me how is this a subsequence? Why isn't this a prefix array? This is still a prefix array, right? Or a suffix array? This is still a suffix array also, right? Do you understand how you will extend the analogy of 1D suffix arrays to 2D? So the way you will extend it is, see, this, if this is the 2D array, then this is one suffix array of 2D array. This is another prefix array of the 2D array. This is another prefix array of the 2D array. Similarly, this is one suffix array of the 2D array. This is one suffix array of the 2D array. This is another suffix array of the 2D array. This is another suffix array of the 2D array. Correct? So this is what is this sub problem then? Basically, you have to find AAC in the entire matrix other than the cell C, other than the cell 00. So in the AAC, in this word, I know what I'm left with is a suffix array. It is a suffix array. What about the 2D? What am I left with? I am left with a subsequence, right? What is the subsequence of the 2D array? A subsequence of the 2D array is basically one or more elements from the 2D array you pick. So whatever you are left with, whatever you pick, you put a 1 in those particular positions and zeros in others. This is a subsequence of the 2D array, similar to like 1D array. So first of all, for 2D arrays, is subarrays and subsequences clear? Like pictorially, do you get a feeling of how subarrays and subsequences look like in a 2D array? Right, everyone gets it. 1D array, it's still easy, but 2D array, you should be able to understand subarrays, which are like these are subarrays. Similarly, this is one subarray. So you are left with a subsequence of the 2D array, a suffix array of the 1D array, and now you are at this starting point. Correct? So what is the sub-problem then? The sub-problem then reduces to find AAC in the matrix A, or let's put it this way. The sub-problem in English, just think about the sub-problem in English. It is find AAC in the, or from amongst the unvisited elements of the matrix A, starting from 0, 1. Right? Isn't this the sub problem that we reduced to in English? What was the original problem? The original problem was find CAAC from A. Basically, to begin with, it was from A, basically unvisited elements of A, but everything is unvisited to begin with, starting from 0, 0. Right? This was the actual problem, and this is the sub problem. Everyone gets the sub problem in English? Does it make sense to everyone? Yeah, Akash, I will repeat it, don't worry. Did everyone get the sub problem? How did I arrive at the sub problem in English? Yeah, Akash, don't worry, I will come back to that. What about others? Yes, I can tell you. So if you remember, what was the algorithm? How did we go about the process? We said that first I will find the starting position in the array in A, from where to begin the search. Okay, this is the first thing that I did. So I found out that 0, 0 is a position from where I can begin the search, because 0, 0 had C and my word also begins with C. So I knew that I have to start with 0, 0. So what was my original problem then? My original problem was find CAAC in A starting from 0, 0. Right? This was the original problem that I am trying to solve. So now for this problem, I told myself that the decision is that I can go in 4 directions. So how do I arrive at a sub problem? I arrive at a sub problem by taking that decision and seeing what am I left with. And that's how I think about the sub problem. So let's say I take the decision of going to the right. So what am I left with? I am left with finding AAC from the entire matrix A, but I cannot have C again. So I am now my search space is this matrix. from the matrix A prime, which is basically A minus 0, 0, index. So I have to find AAC from in A prime, and I'm assuming that I have to starting from 0, 1. Isn't it? This is how I can write my sub problem along similar lines as the original problem. Right? Is this now clear, Sai and Akash?
Yes, sir.
Yeah. So now you see, if this is the sub problem, now I want to represent this sub problem, correct? So how do I represent this sub problem? I have to represent AAC. How do I represent AAC? It's a suffix array of the word, right? So I can represent it by a word and a start. I'm just deciding the arguments of my function now. So pay attention. This is how I can represent this suffix array. Now let's move on to this part. From amongst the unvisited elements of the matrix, I have to find AAC. So how do I represent the unvisited elements of the matrix? I can represent it by the original matrix and a visited matrix, correct? So visited matrix will have ones in all the places which elements have already been processed, and it will contain 0 for all the places whose elements have not been processed. Correct? So this is how I represent this part of the problem, the sub problem. And this is nothing but a subsequence of the original matrix. And finally, how do I represent this part of the sub problem? Starting from 0, 1, I can just say start in, start j. So these are the parameters of my recurrence relation. Just the first part. I told you there will be typically 3 types of parameters: the actual parameters which change, the recurrence relation parameters, the result, and the contribution. So this is just this part. Do you get this? How I arrived at this? You should be able to understand how I arrived at it.
Sir, what is the A there?
A is the matrix.
Whole matrix or without the first?
A and V together represent this part. The matrix without the first element.
Okay.
Correct? Do you get it? Can I have acknowledgements if you get it? If not, I can repeat. So I'm just taking one more way of like solving problems wherein I told myself. So this is just another way I have taken, another route that I have taken, wherein I told that first articulate your problem. Articulate your problem in English very precisely. Like this articulation should be very precise. Then think of a decision. A decision that I can take. After that decision, what am I left with? Articulate that. After the decision, you will be left with a sub problem, correct? So now you articulate your sub problem in precise English. And from here, when you articulate it in English, find a representation of the for the sub problem. This is the route that I took for this question. It's 1-0. Yeah, it's 1-0. It's 1-0. My bad. Sorry. Yeah, it's. I was taking this as the first row. So this will be 0-1 only, right? I am correct, right? I just took the decision of going to the right. When you take the decision of going to the bottom, it will be 1-0. So there are 4 sub problems here, right? Because of 4 decisions. So for all those 4 sub problems, we will have a different start point and a different correct? So I am just telling you how did I solve this problem? This is another way to come up with recursive solutions. You can articulate your problem in English, think of a decision. Decision is always there. Once you have a decision, take that decision, and then you will have a sub problem. Articulate that in English, and from there you should be able to find a representation for the sub problem. So this is for, like, this approach really helps when you want to find a representation for the sub problem, because till now what we have been doing was our sub problems were like quite trivial, not very trivial, but at least they were not very hard. So even without articulation we were able to represent it, right? Because we just had an array and a sum, and we used to say that, okay, now what you are left with is sum minus ai starting from this address. So we did not really articulate it in English properly or wrote it down, but we knew that, okay, now my sub problem is this suffix array and this integer. So now as you get into higher dimensional sub problems, like for this case, if you see, the sub problem is 5 dimensions, I think, so, or 4 dimensions. So when you go into higher dimensional sub problems, it becomes increasingly difficult to think about all the parameters your function should have. And in that case, it becomes very important that you think in this direction. Once you articulate your sub problem in precise English, you will be able to logically define the parameters of your function, which can take part in the recurrence relation. Yeah, Akash, I will give it. So this part is now clear to everyone. What are the parameters then? I just articulated my sub problem. I was left with a suffix array of the word, so that I can represent with the word and a start index. I was left with a subsequence of the matrix, which I can represent by the array and the visited, and I was left with the start and the end, which I can represent with I and j. So this is all the parameters that needs to go in my in my sub recurrence. Right? All good? Can I have acknowledgements for people who understand? Again, understanding not with respect to what I'm saying here, but understanding as to how I came up with this. It's important that you write this on your own, and that's why this is very crucial. Yeah, I have the coordinates ij. That's the starting point. Start I, start j. Okay, so this is then the first. So now we have done the 2 steps wherein we took the decision. We have a sub problem. Now let's write the recurrence. So now I know in my recurrence what all will need to go in. F word I, which is then the matrix, let's call it A. Then the visited, let's call it V. Then let's SI and SJ, start I and start J. So this will basically be, it will be an OR of, right? It will be an OR because you can go in those 4 directions. If in any direction, if you find the word, then it's true. So that's why I have taken a Boolean or a logical OR of one second, Divya. W, you have 4 possibilities, right? In V you will mark ij as true. So this will be V union Vij as true, comma 1 will be Si plus 1, Si plus minus 1, Sj plus minus 1. This will be like the 4 cases. Does this make sense to everyone? I just marked that particular cell as visited, and I now am, my sub problem is Wi plus 1, which is basically the suffix word, this subsequence, and 4 possibilities. I plus minus 1, j plus minus 1.
Sir, what is that? V, U, and V, I,
This
J?
is just like I have written it. It's I in the V, in this original V. So let me put it this way. This is V prime then. And V prime, where V prime is nothing but V. In addition to that, you take you take the entire V, and you basically in that V you mark ij also as true, and you take basically it's not technically a union, but just to make you understand, it's basically in V prime is basically V plus Vij is true, those two things. Okay, Jadav, did I
Okay,
answer your question?
Yes, sir.
Yeah. So let me know if you don't understand the recurrence. Divya, if we are using coordinate start ij, then why are we using start in the func parameter? What func parameter?
In the previous relation, I think.
Make this cave, it is really confusing you. We have three, Divya. We have, this is basically the start of the word, the index from where I will start the word. And this is for the start of the matrix. Yeah, so that's why it's a good exercise to articulate it in English. When you articulate it very precisely in English, things will be fine. And make sure that you adhere to that articulation in your recurrence also. All right, is this clear to everyone? Can I have some acknowledgements from people if you understand? Okay, so then, so that's it. Basically, this is step 2. Let's talk about, after you have done the recurrence, let's talk about the other parameters. Why are we taking OR? Because we are at a particular direction, a cell current, and we can go in 4 directions: right, up, left, or bottom. And if you are able to find the remaining word AAC in any of the 4 directions, then you should return true. That's why you have taken a. So let's talk about the other parameters of the function that we were talking about. Let's talk about the contribution. So is there any contribution here from a particular recursive index? Count, what count, Drishan? There is no contribution, right? Your everything is fine, right? I mean, because typically problems wherein you are expected to only return true or false, there won't be a contribution. When you have to enumerate things, you will have contributions. And then finally, the return type. So what is the return type here? Boolean, correct? So it's fine if we take it explicit. I mean, you can take it implicit, but because it's just a Boolean, it does not hurt to make it explicit. So then if I have thought about these parameters also, then my eventual function prototype becomes bool f this entire thing. Ashra, explicit, this is explicit, wherein the function is explicitly returning a value. Implicit is when you return it in the form of an argument into the function, like pass by value, pass by reference. Yeah, so we have been discussing over in the past 2 classes, the cases when we should actually have a void return type here and return implicitly from the function. So typically when you have to return large amounts of data like an array or let's say a 2D array, you should avoid having an explicit return type, because every time you return for a recursive function, a new copy is created. Instead, just have one global copy, and not really global, one copy of from the main, and use it everywhere. So this is the argument and this is the function prototype. Let's talk about the base cases. Tell me, what are the base cases? So base cases, as I told you, there will be two types of base cases, positive and negative. And how do you think about base cases? You typically think about the variables in the recurrence, and you think about what are the smallest values, like smallest problems corresponding to each of them. Sakshi, what is the question? What will we go in each direction if we find the next letter adjacent to it more than one time? I did not get the question. Maybe you can unmute and ask. So let's think about the base cases in this case. You have A, you have the word, the start of the word, you have A and V, and you have SI and SJ. So one thing is K can reach the end of the, correct? K can reach the word size. This is one. Let's just think, what are the possibilities? For this, what is the smallest subproblem for a suffix array? The empty array, correct? So K is W dot size. Okay, let's talk about this. What is the smallest? When everything is visited. The smallest subsequence is an empty subsequence when everything is visited. Let's write that. We will not be needing it, but let's write that. So visited ij is true for all ij. What is the third? SISJ. So what are the base cases for this? The start index.
End index also.
Yes. So it can go negative or it can become greater or equals n. Sj can go negative and Sj can become greater or equals m. So these are basically the base cases. I just looked at the arguments and arrived at the base cases. So now let's think what will be your result in each of the cases. For this case, what will be your result? Yeah, true. Because I have, what does that mean in English? It means that you have to find an empty word in an array. So an empty word in an array is, you will always find it. Okay. Let's talk about this.
Sir, in the previous one you told, like there cannot be empty array also, right? Like W dot size means it's a whole the word size, right? We can.
Yes. So because it's a suffix array, what does that mean? See, K was the starting index. So if the starting index is this, then the array is empty, right?
Yes, sir.
If the starting word is this, then this is the array. Starting word is this, then this is the array.
Okay.
So if the starting word is this, then it's an empty array. If the starting word is this, then you have just one cell as the array.
Okay.
So for these cases, let's see. So if at any point during the search, if you reach the end of the board, what does that mean? That means that you cannot find a word now because you cannot proceed. Similarly, if you reach here, then also you cannot find a word. If you reach here, then also you cannot find a word. If you reach here, then also you cannot find a word. Right? So these will be false. What does that mean in English? If you were to ask, you are saying that if I start outside the board and I have a matrix and a word, can I search, will I find the word in the matrix? No, you will not find the word because you cannot start outside the board. Right? So if you treat it as an independent problem, do you understand how this is a false? Yeah, so all the base cases you should think like that, just independently. Similarly, here our problem was, I have a matrix. If I have an empty word, will I be able to find it? Irrespective of where I start from, I will always be able to find it. Correct? So that's why we return a true. So what about this base case? What do you think? Will this ever happen? If assuming that the word is small compared to the matrix, will it ever happen that you will have all the cells of the matrix as true? It will not happen if the word size is smaller than the total number of elements in the matrix, right? Because for every character of the word, you are marking one index as true. So it will never happen that if the total number of elements in the matrix are more than the total number of characters in the word, you will have all trues in the matrix. Right? Do you see this? So this will not happen, which means an empty subsequence is not possible in this case. So these are basically the base cases and my results on each of the base cases. Now ask me questions if you don't understand anything. And if you remember, we were talking about the order of the base case. We said that we should write positive base cases first. Why is that? Because if we write this first, then we will have to bifurcate it into two cases. That even if I am out of the board, if I have to search for an empty word, I should return true. Right? Do you see this? Why I have written the positive base case first and the negative base case later? It's just for the ease of coding. Otherwise, I would have to, within this base case, I would have to split it into two cases, empty word and non-empty word. For empty word, my result would have been true. For non-empty word, my result would have been false. But if I start from the positive base case always, here I mean that no matter what the values are for the other parameters, I don't care. I will always return a true if I get this. And if I go here, that means this is not true. Definitely this is not true. So now I can take care of other cases. It's like a decision tree, right? You take a decision and you handle one case and then you handle n-1 cases here, like this. If we are at C and we find A to the right, where are you coming from, Sakshi? If you are at C, let's say you are at C here. You are saying you have an A here and you have an A here. So what is the question? Shashank, subsequences base case is basically this. What is the smallest possible subsequence of the 2D array? Empty subsequence. When will that happen? When all all the elements will be visited. Correct? So this is the smallest subsequence. Now I am just arguing that this smallest subsequence will never happen because my word size is less than the array size. The total number of elements in the 2D array is greater than the word. So it will never happen that I will fill everything in the array as true in the visited array. Because for every character of the word, I am filling one cell in the array or marking one cell in the array as true. Right, Sasank? That's why I am asking you, Sakshi, where are you coming from? Are you coming from the top, or are you coming from the right, or from the left, or from the bottom when you are at C? If you have come from the right, you will not revisit for this I. Why? Because you have marked this as visited. Now you have to search in the remaining array. That was the sub problem. If you are coming from the top, then yes, you will go in both the directions. If you are coming from the right, then you will not go to the right. Yeah, if C is your first letter, you will go in all the 4 directions. Is this part clear to everyone so far? Sasank, were you able to hear? Because, or are you still facing issues with your internet? Others, are you clear with all the base cases and the logical reasoning behind each of the base cases? How we arrived at a decision for them? How like did we enumerate all the base cases? How we arrived at a decision for each of the base cases? How we arrived at an order for the base cases? All these things should be clear to you.
Sir, if word size is greater than the matrix size, then the subsequence we can come to false, right?
The subsequence can come to or everything can be true then, yes. But that will not happen, right? You can return false in that case anyways, because that word you can never find in the 2D array, right?
No, sir. Like if there's a big.
So when I say a matrix size, I mean the total number of elements of the matrix. So let's say you have a 2 by 2 matrix wherein you have A, B, C, D. And now if you want to search for A, B, C, D, E, will you ever get it in the matrix? No matter what?
No.
Right? So that's what. If your word size is strictly less than the total number of elements in the matrix, it will never happen that you will mark all of them as true, because every cell is marked for a corresponding index of the word.
Okay, sir.
Sir, if we have more than one A, then we will mark both of them as true.
That's what I said. We are doing it in 2 steps. The first step, I find all positions. Let's see the code, you will get it. Find all positions from where to start the search. And for every such position, we have to do all the story that I told you. Let's see the code. Things will become clearer to you. Okay. So let's do the phase 1 first. So first and foremost, I will have the sizes. This is the row size. This is the column size. Let's have the word size. And let's have 2 indices. First things first, what will I do? I will increase the font size. And I will, let's start. So first things first, I will find all the possible start indices. How do I do that? I can go over the entire matrix and I can check if the board if this is the case, then I will call my f, whatever my f is. So let's write the f, or let's complete this first. We will have a visited of size n by m. All initialized to false to begin with. And now let's write the file function. So I told you function I can have explicit return type because I am just returning a primitive value. Then let me have the word first. So the word suffix array will be in string word and int start. Let's say start w, which is start word. Then we will have the subsequence for the 2D array, the board and the visited. And we will have the start I and the start j. So I will implement this, but basically if I come to this, what am I doing? I will have a result. If it is found, then I will do the call this function. This is step 1, what I am doing. And what here I am doing is step 2. If you remember the step 1 and step 2 that I told you in the code, in the explanation. So now we will call exist helper with this word start will be 0, board will be board, if you are able to spell it out correctly, visited will be visited, start I and start j will be I and j. If I find it, then there's no point in finding the next possible start index, right? I can just return true from here, just an optimization. And from here, I can return false. So this is my step 1. Let's talk about the step 2. Let's write the recursive step first. So what is the decision? The decision is 4 possible directions where I can go. So let's take all the 4 directions. So I can simply return exist helper word start w plus 1. In the recursive step, I will first mark this particular as visited. And let's try all the cases. Start I plus 1, start j, or four ors. Let's change, this will be minus. Then in the third case, you will have plus 1. Fourth case, you will have -1. So this is the decision. And finally, I will undo the change, which is I will mark my visited as false. Let's come to the base cases. Positive ones first, which is if your start W has reached the end of the word, then you can return true. Now you have negative cases, which is if this becomes negative or this becomes greater equal sign, return false. Let me just find out the n and m as well. So n is visited dot size, m is visited 0 dot size, and the third case is if start j becomes less than 0 or start j becomes greater equal sign, then I have to return false. That should be enough.
Sir, I have a small doubt.
Yeah.
In the recursion function which you wrote above, this undo the change part, that need to be like before the return statement, right? I mean, जो return वाला part है उसको variable में डालना होगा और फिर undo करके फिर return करना होगा.
सही बोल रहे हो आप. That's true. हाँ, मैं समझ गया आप क्या बोल रहे हो. मैं कर दूंगा उसको. ये बोल रहे हो ना आप? हाँ. Yeah, that's right. लाइन 5 में क्या लोड हो गया इसको? यहाँ पर एंड नहीं लिखा है.
So why are we undoing the change? I don't understand.
Yeah, we will come to that. That will be the subject of next half an hour discussion.
So we should also check for the case when we revisit a visited cell.
Yes. You're right. Let's discuss that. I missed that somehow. Let me just finish it, then we'll come back. This is because
so we need to check whether the word is what we are looking for.
Yeah.
The later, I mean.
Yes, those cases we have left out those cases. A lot of cases. This will also go in the base cases. Let's go. Let's discuss these two lines. We will discuss this line and this line. We have not talked about these two lines.
So what the case of the word size greater than the board size? Like,
come again?
Like where the word size of the word is greater than the m cross n of the board.
It's given that it won't be that case most.
In that case, you can't able to form the word, right?
Yeah, you will not be able to. So if you see this, I mean, it's there in the test cases that they have taken care of that. But yeah, you should ideally take care of that here somewhere. That if you get a, I mean, that will also be taken care of here, right? Because there will be a point when you will move out of the board, right? And then you will start returning false. So I guess that case is taken care here.
Okay.
Let's discuss these two things, but other than these two, I guess it's straightforward, right? Whatever we discussed. This is what we call pruning. We will come to this. These two are backtracking concepts. So we will talk about this. This is not technically a base case, but this is a pruning that you have done.
Sir, in line number 8, why m is equal to visited, 0 index is taken there, like not in n.
The first row, I'm just taking the
Is
size
it
of the
like
first row. So this is the number of columns basically. This is one way of finding the number of columns. Do you understand? Because it's a 2D vector, right? With 2D array of arrays. So when you take the size of the first 1D array in that 2D array, what does that give you? It gives you the number of columns. Should I write it?
yes, sir.
This is this basically. You have this. So this, if you take this, so this is nothing but in pictorial, it is this. You have a 2D array, 1D array of arrays. So when you take this original, let's say this was m, when you take m dot size, it gives you the number of 1D arrays, which is nothing but the number of rows, correct? Number of rows or number of 1D arrays. And then if you are talking about m0, you are talking about this array, correct? So when you do m0 dot size, what does that mean? That means that you're talking about the number of elements in this. So which is nothing but the number of columns.
Okay, sir. Got it.
Right? So I'll just keep the screen for some more time. Other than these two lines, if there is, other than this pruning line, line number 17 and 18, and this line, the other than the highlighted lines, if there is any question in any of the other lines, we can talk. Otherwise, let me know and we can move ahead with these two. This will basically be a entry point into backtracking.
Sir.
Yeah.
So in pruning, that's why we're checking if the word if the alphabet at the word index is equal to the board index.
Mm-hmm.
So like you'll explain that, right? Is that how like we know that the letter is present in both the word and the board at that particular point?
Yeah, let's come to that. Let's draw the decision tree for this, and things will start becoming more clear. So let's draw the decision tree for this, and it's a complicated one, but let's draw a small one. Let's say you have the task of let's say you have the task of finding give me a word. Let's find OFO. Okay. Let's discuss pruning. Let's say you have to find this word OFO in a matrix. Let's take a 2x3 matrix, and okay, let's take this is X. Let's take this as F. This is F. This is O. Let's take this will bring out pruning. I'm just thinking. Let me. Yeah, it does not matter. Let's take another O somewhere. Let's take O here, and let's take X here. Let's say this is basically. So just follow now. I'm just trying to draw a recursion tree. These things will become more clear with this. So let's say this is the matrix, and in this matrix, let's say Prakhar wants to find OFO. Okay. So first, in the first step, we will find the, we will come to pruning, Akash, don't worry. We have not discussed it. So in the first step, what are you doing? We will find the occurrence of O. So what are the places? Oops, just a second. So we will find the first occurrence of O in the matrix. So we will go row wise. We'll go to this. No O, no O, no, no. Now you get an O. So you will now start your function from this. Okay. So 4 cases. You can go to the top. You can go to the right. Top, down, left, right. If you go to the top, you are left with, you mark this as true. So you are left with false, 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 false. This is the true. This is the visited vector that emerges. You are now at this index, and the word that remains is FFO. If you go down, then you will have the same, basically the same matrix, FF, F, T, FF. This is false and true, by the way. And you will have FFO, but you will be at here. Your position will be here. And if you take the left one, you will be again F, 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 T, F, F. Your position will be here, and you will be left with FFO. And finally, the fourth case, when you go right, you will be left with true, false, false. You will be here, and your remaining word will be FFO. Okay. So now let's see. Now, when you are here, think about this case. You are out of the matrix, and you have to still search FFO in this remaining, amongst the remaining falses. So is that possible? No. So you will terminate. Similarly, here you are out of the board. You have to search FFO. You cannot search. So this is again gone. Let's talk about this case. Now, when you are here, you have to now look for F. So now you know that F is not possible. It's not possible. F is not present here, correct? So as per the constraints of the question, if you go along this path, you will not be able to find a word, right? So what I'm saying is there is no point going further below. And the final case is when I am here, so I have X, the same case as this. So then there is no point going here. So for this start index, I was not able to find the word. So then we move on. Now we go back to step 1 again, and we find the first address after this with an O, which is this. So now let's begin with this. So now you have X, F, O, O, F, O, and there was something else here. You had an O here. So now you are at this index and you are starting all over again, and you are here in the word. So you have 4 cases. In the first case, you can choose to go left, you can choose to go right, left, right, top, down. So if you are going left, then you will have F, 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 T, F, and you will be here and you will be left with OFO, FFO. If you take a right, then you will have same FFF, FTF, FFO, but you will be here now. If you take top, you will be having FFF, same FFF, FTF, FFO. You have to search, you will be here. And when you take down, you will have FFF, FTF, and you will have FFO, but you will be here now. So let's talk about this case. This is a base case. You have reached a position outside the board. So if you are outside the board, you cannot, if your start index is outside the board, then obviously you cannot search for this word in the board. So this is not possible, you return. Let's talk about this case now. If you are here and you are looking for FFO, so you are looking for FFO, you are here now. So you see that if I go down this path, what words will I be enumerating? I will be enumerating, every word that I enumerate will have an O in the middle, will have O as the second character. So I can go ahead and enumerate it. It's fine. Nobody is stopping me from enumerating till the word of length. But I know for sure that none of these words will actually match this word, because the second character in all these words is O. So I say that there is no point in going down this path. And this is what we typically call pruning. I will define it formally, but let's talk about the other cases first. Now let's say you are here. You are here, the same case. Now if you take down this path, all the words that you enumerate here further will have O as in the second place. and you know that none of these will match the original word that you are looking for, because the original word has F in the second place. So there's no point in going down this path. You can still go down this path. These are all valid problems, but you won't. That's why this is called pruning. Here you see that the second word is also F and the character is also F. So you say fine, this is fine. So I will go ahead and I will mark this as true. Now from here I have 4 possibilities. I can go left, right, top, down, same. So I will again keep going, and eventually if you go right, and then from right if you go down, which will be the 4th one, here you will be finding the word. Here you will be able to find the word and return true. So this is how it is working out. When you are here, let's do one more step. When you are here, you know that if you go down, you will be reusing an element again. Correct? So what I'm saying is, when you are here now, let's talk about this case. If you take this case, when you are going down, what will be the sub problem? You will be left with FTF, FTF, and you will be left with FO to find, and you will be here, this cell. So when you are here at this particular cell and you have to find FO, this is again not a valid sub problem. Correct? Because why? Because you said that I will only, my problem, sub problem was to find it from all the unvisited elements of the array. But this is already visited. So I cannot have this as the starting point or for the next character. So you say that this is also not possible. So you will typically return from here also. So there are two things that I tried to highlight here in this running. You were enumerating a tree, a decision tree, and generally, let's look at recursion in particular. So in recursion, what you do is you enumerate all possibilities. Okay. So here also what you are doing is you are enumerating all possible possibilities for a particular problem. And then you are saying that, okay, what I will do is I will enumerate all possibilities, and out of all these possibilities, whichever are valid, I will take them. Whichever are invalid or bad cases, I will not take them. That's basically the strategy that you are using in recursion. So this kind of a programming paradigm or a programming approach where you are enumerating all the good possibilities as well as bad possibilities, and what you are doing is when you reach a bad possibility, you go back and then you enumerate another possibility. So think of it as, let's say you are in a jungle. This is a jungle. You enter the jungle, or you are in a maze and you have to reach a particular destination. Here is your home, and you know that you don't know the way out to your home. There are like multiple openings. Some of them open here, some of them are dead ends. So to reach home, what is the strategy that you would apply? You would have a rope that you will tie to yourself, and maybe you will tie to the starting point. Let's say one of the trees here, you will tie it. And then what you do is you will then start walking. And every possibility you will encounter, you will take that. Once you take that possibility, if you hit a dead end, what you will do is you will follow the rope. The rope was coming with you, right? So now you will follow the rope to backtrack. and reach a point from where you can take another possibility. And then again follow the rope, come back and take another possibility. So this type of a programming approach wherein you solve problems by visiting all possibilities, some of which are good, some of which are bad. When you visit a bad possibility, you backtrack. Backtrack in the sense you step back and you rethink your possibility and go to another possibility. This type of programming approach is nothing but backtracking. Recursion, if you see, recursion fundamentally is just a function calling a function, nothing else. So backtracking can be achieved by recursion. It can be achieved by iteration also. You can have a stack and you can still be able to backtrack. It is just one way of solving problems wherein you enumerate all possibilities, you reach a bad possibility, and then you go back from the bad possibility and then explore another possibility. This is what is called backtracking. And typically we use recursion for backtracking. That's why these concepts are generally like not distinguished from each other and talked about in together. First things first, do you understand what is backtracking and what is its difference with recursion? Did anyone understand the story that I told you now? Everyone understood it? So from today, you should not have any confusion or as to what is recursion and what is backtracking. Recursion is just one way you can achieve backtracking. Recursion fundamentally is just a function calling itself. That's it. That's what recursion is, nothing else. That's recursion. Through recursion, you can solve a variety of problems. And we say that through recursion, you can solve one class of problems wherein you do this, wherein you go, you come back, you go, you come back, which is what we call backtracking. So now, if backtracking and recursion is clear, then let's talk about a backtracking solution. What do you think, Rishabh? Have we been doing backtracking? We've been doing both, right? We've been doing backtracking using recursion. Most problems. I will have to think which ones we don't. Yeah, I mean, fundamentally, you can say that every time we pop back. So now let's talk about a backtracking solution. So we were talking about recursive solutions and we said that in recursion at a very high level, what you do is you enumerate all possibilities and every possibility that sits at the leaf node is a base case. Correct? The smallest subproblem. Now we are saying that in backtracking, there is one more concept which is called pruning, where you say that when I am enumerating possibilities, if at any point, if I am able to make a decision that if I go down this path, any possibility that I enumerate will be a bad possibility, then I can choose not to go down this path. And this is what we call pruning. Okay. First of all, do you understand the English definition of pruning? We will see it in action in the question that we've been talking about. But in English, do you understand the difference between a base case and a pruning? Base case is the smallest subproblem, because in recursion, when we are doing a backtracking solution using recursion, what will we have? We will have subproblems which will diminish, and there will be a point when you will reach the smallest subproblem, and that's basically the base case. So base case comes from recursion. Now in backtracking, you have another possibility where you can terminate early. And that is basically when you make this decision that if I enumerate anything below this, I know it will be all bad. And that's what we call pruning. For instance, if you remember in the OFO example, we started with O, we there was a case when if you take left or right, you will, this, let's say this leads you to O4. This leads you to OOF. So technically you can terminate here because you know that the anything you enumerate below this will have OO as the prefix. But you are looking for O4. So you can terminate here early itself. And that's what is called pruning. And so if you see the case, we did not enumerate all possible words of the matrix starting from that index of length word. For some of the words, we preempted even before we had enumerated the word completely. Because of this intelligence or this idea that I had, that if I encounter this O, I know that every word that I go down this path in the leaf nodes, all the words will have OO as the prefix, and then there's no point in going down this path. And that's what we call pruning. We say that, okay, then don't go here. There's no point in going. So this is not a base case, but it's just that we are terminating early. Okay, pruning is clear to everyone with the example? What about others? Do you understand the entire story that I told you? Pruning, backtracking, a guy lost in a maze. So then tell me, if this is what is pruning, then the if that we had, wherein we had, so if you remember, what are the ifs that we wrote in the base case? In the base cases, we wrote about I and j becoming 0 or n or m. We wrote about we wrote about the word dot size and start index becoming equal to each other. And then we wrote about the current alphabet not becoming equal to the current alphabet in the matrix. This is K and this is I and J. So this was pruning. What about the fourth one, wherein we said if not visited? What is this? Is this a base case or is this pruning? What do you think? What about others? Is this pruning or is this a base case? Can anyone unmute and tell me why?
So that is pruning because this is basically if we have already visited that path. So if we have already visited that path, which means either we have got a solution or there is no solution. So we don't need to go down that path. So we can cut off that branch if we ever reach that in our solution, like while moving.
Is that a pruning?
Or
yes.
Yes.
Is it like a problem? So is it like a sub problem which is not in our domain? It's not a valid sub problem, right? What was the sub problem? The sub problem was that I have to search for the remaining suffix word out of the matrix of all unvisited elements. Right? That was the sub problem. So if you go to a cell which has been visited, is this state of recursion, is this a valid sub problem? Do you get what I'm trying to say? Whatever you enumerate, these are all valid sub problems that you are enumerating. Correct? Are you still taking time to digest this? Did anyone understand why this is not a valid subproblem? Because our subproblem was basically we have to find the remaining alphabets of the word. We have to find the remaining alphabets of the word from all the unvisited elements of the matrix. That was the problem, or that was the subproblem. So this is not a valid subproblem. So in this entire enumeration, it should not really be coming. Right? So when you are here, you will typically be going in. Now ask me questions if you don't understand this. So that was basically the reason behind that. It's not a valid subproblem, so you should not obviously enumerate it.
Actually, could you repeat this pruning thing and subproblem, because my network was, completely disturbed. It's not so clear.
Yes, Ravan. Anyone else want it to be repeated? You want it to be repeated, Tanya and Karan, or you are good? You want it to be repeated? Yeah, which part? Yeah, I can repeat. It's fine if many of you want it. So, do you understand the difference between recursion and backtracking? Like, do you understand what backtracking is first? Karan, do you understand what backtracking is? Yeah. So now see, we told that when we are writing a backtracking solution, what are we doing? We are enumerating all possibilities. So we have all possibilities that, so you have a problem, and what you're doing is you are reducing your problem into smaller problems. You are enumerating all possible possibilities for the answer. So all these possibilities will typically be here. And what you are saying is that I will visit all these possibilities and handpick those possibilities which are good for me. That's what I am doing in backtracking. So now we said that there are two things. There are base cases. So base cases are basically, so this was a problem. And to solve this problem, what you were doing was you were reducing the size of the problem. And finally, you reached a state wherein you couldn't break down the problem anymore, and you deduced when you reached here that whether this is a valid possibility or not. So this particular case from where you start returning is called a base case. And in backtracking, there is another concept of pruning, which is basically that if you are at a particular node, and if you know that even if I enumerate all other possibilities from this node, all these will be invalid. No matter what, if you have that knowledge right here itself, then there's no point in going down these paths, right? So that's basically what we call pruning, wherein we avoid a particular branch from expanding further because we know that it will only lead to bad possibilities. So that is what is pruning. We have not yet reached the smallest problem, mind you. We are still at a very big problem, but we are still returning from here, or we are not going down further because we know that from here, if we go down, it's all bad. And that is what is pruning. So do you understand the difference between a base case and a pruning? If you see the example, if you see the example, we had the base cases where basically when you said that you run out of the board, or when you finish expanding the word, when you are there, then it's a base case because you cannot expand further. It's like one smallest sub problem for which you can solve. So that's the base case. And if you see in that, there was another if wherein we were checking if the word of that current index k, if it is not equals to a of ij, then we were saying that this is you return false from here also. This is what is a pruning, because I know that if at this particular index, if I get any other character other than f, then I know that no matter, even if I go down this path and start enumerating everything below, I know that I will never encounter a correct word, a valid word. So I know that there's no point in going below. So this is what is a pruning. And then I asked you that, okay, this is the pruning case. What about this case, wherein you were saying that if it is already visited, then return false? What was this? So for that, we said that this is basically nothing but this is also a kind of a base case. This is not a valid sub problem after this. So you have why is this not a valid sub problem? Because our sub problems were, what do you think? Is this pruning? If your problem is that you are expanding all possibilities from the remaining elements of the matrix, if that is the possible problem, then this is definitely not pruning. If you are only considering the remaining elements of the matrix, then it's not even in this picture. It should not even come in this picture. So you can say it's some sort of a base case itself. Like you have reached the, it's not really a base case also, but I think you get the idea, right? Any more questions? How is it different from returning the empty array? For example, if we didn't sort in the maximum sum, no, I don't get your question, Karan. So this is what is pruning. Now let's see. All good so far? Let's see. In backtracking, what we said was, I will go to a state, I will expand all the nodes. So we said that once I reach a bad solution, what will I do? I will come back and I will then explore another solution, right? This is what I said I will be doing in backtracking. So when you return to the previous recursive step, so let's say this was recursive step I and this was recursive step I plus 1. When you return to the previous recursive step, you should restore the state of that recursive step. What I mean by that is that let's say you are at step I, you have a certain state, which means that you have some variables which have some values which you have assigned to them at step I. Now what you do is, now let's say you increment x and you go to I plus 1 now. Now you have gone to step I plus 1. So now with this x, so this x, let's say it was 3, you did an x plus plus, now x became 4 in step I plus 1. So good, now you go ahead and you enumerate all the possibilities. But now when you return from I plus 1 to I, you should, after you return to I, you should restore the state of x to 3. Why is that? Because now let's say from step I, you are going to another possibility, I plus 2. You want to, the decision that you have taken to go from I to I plus 2 was on the basis of this state and not on the basis of this incremented step. This incremented state you only did because you wanted to go to this step, and it helped you to go to this step because this was the state for this step. That's why you incremented it. So once you come back from this path, you should restore it so that if you go to the next step, you should have the same state of I as it was when you had made the decision. Because every decision that you make from I assumes a certain state of I, right? Every decision that you make, it has a certain state of I. So if you are changing that state at any point, then and making a call and going to I plus 1, then when you come back from it, you should restore it so that when you go to I plus 1, there are no side effects of that. And that's basically what we do in all the popbacks that we have done so far, or even in this case, when we are unmarking it, when you are marking that visited as false, this is what we are doing. When I was at state I, my visited ij was false. This was the state. And from here, I had made the decision that except this cell ij, for all the other cells, I will now search for the remaining part of the word. And so I told myself that one way of doing it is I could mark this as true and search. So now when you come back and now when you have to go to this step, you should restore it to false again, right? And then mark the corresponding another cell as right. So this is what we were doing in backtracking when we are restoring the states.
So can you show like in the code for this question what we did for that undoing the changes runner step?
It was this step. This step.
Okay, so it was just setting it to false.
Yeah, because the our state we have only changed. See, our state is defined by this. This is how you define the state of a stage or a step. And if you change the value of any of these variables, you should undo it so that when you take the next step, it should not affect your answer. So here we changed the visited, right? So the state changed. So when you come back, you should undo it. Does this make sense? What about others? Sai, do you understand the fact that you have to explore when you come back from a possibility that you have explored, you have to explore the next possibility, right? That's what backtracking is. That's what we said we will do in backtracking. So if you have to do that and you have to explore the next possibility, then how can you, when you explore the next possibility, you should be restoring the state of the previous step to the same state as it was before you had explored that path, so that the next path you explore will be consistent. And that's what we are doing here.
Why there is false then? Equal false.
Because it was false when we entered. right?
What? Because it was false when we
entered. When we entered this state, it was false.
Okay.
It's just that for our convenience, we made this true, so that these steps would have been, what you could have done is you could have created another visited Boolean vector of 2 dimensions, and you could have copied everything from there to from visited to that particular vector. And if that vector for this index start I start j, if you set to true, then you don't have to undo. Everything is good. Okay, everything clear in this code in backtracking?
So good and bad possibility is not just like in this backtracking problem, it's not just those leaf nodes. It can be any of the nodes in the middle also, right?
Depends
like that
on
could
the
also
problem.
be a bad possibility. Okay.
Yeah, I mean, it depends on the problem and how you are defining the problem. If my problem here is that I will enumerate all 4 length words in the matrix, and those are all my possibilities, then some of them will be good, and then all the leaf nodes are my possibilities. What is the question, Akshay? Only if it returns we have to undo. What does that mean?
So like if there is anything is wrong, then only we are backtracking and making it false, right? Like when it returns false or true, then we're backtracking it and then making it false.
To go down the next path.
Huh.
Okay,
so like I just want to ask if that is the way we're doing it.
You have to undo, I think, every time. Are you saying that we have to undo only for certain cases?
Yeah, like for example, if we are not getting the desired word, we have to just backtrack and keep on undoing it. And once you get the desired value, then we can just return it and then say we got the word. We don't need to like backtrack it and make it false, right?
Yeah, I mean, but this is always a safer bet, right? Doing this will not harm that possibility also.
Okay.
I mean, you can get away by not doing it. Any more questions? All right.
Sir, why you're not setting the first row to 0? Like only we did to m of 0 dot size, like that.
Why am I not come again?
Sir, we wrote like m of 0 index dot size. Why don't we wrote n of that 0 dot size?
A of 0 dot size I wrote.
No. In m cross n.
N cross n, yeah. I am doing n cross n.
Okay, so why didn't you wrote like n of 0 dot size? Only we wrote for m of 0 dot size for number of columns and number of rows.
So what you are saying is you are saying is
a code. Once
I
can
got
you show
your
the code? I can see.
So you are saying I was writing n is a dot size, and I was writing m is a of 0 dot size. Okay, now what is the question?
Like why don't you wrote for n of 0?
N is?
Here in n equal to a of 0, why don't you wrote?
In this you are saying?
In above.
In this, what will I write?
There in 0th index, why don't you write?
Here, if I do A0 dot size, you are saying.
Yes, sir.
Here, A0 is basically the first row. So if you find the size of that, it will give you the number of elements of this first 1D array in the 2D array. So won't it give you the number of columns if all the 1D arrays are of equal length? Like, I did not get your question completely, maybe.
Is there no element of, is there any element of index 0, 0?
There is, this element is 0, 0.
Yes, then we are only initializing like m equal to a of 0, right?
This is size. So for this, no. So for this, if this is, let's say, a grid of this type of a grid, let's say. So in this case, our n is 2 and our m is 3. These are values, integers. These are not pointers to any of the elements.
Okay.
These are sizes, right?
Yes, sir.
So this is not like n is pointing to this element and m is pointing to this element.
Okay, I got it, sir. But in can you go back to the code? I will explain it.
Just a second. Yeah.
Scroll up, please.
Here?
Again. Here in line 33. Why after board? Why there is not? You didn't put like 0 in that index, right? Why there is? Why is it like?
Okay, let's discuss after the class. Okay, it will be better, right? Okay. Any other question? Shall we move on? So the idea of backtracking is clear. We will do lot of questions on backtracking and recursion. On backtracking in the subsequent classes. We have 2 more lectures for backtracking. So don't worry, we will cover a lot of questions. Let's do this question. How do you do this? Any ideas? What is the decision? The solution to a backtracking problem remains the same. it will be the same idea that we are using as we've been doing recursion. In fact, we've been doing backtracking all this while without even you realizing. So how do you go about doing this?
The same way as previous problem, but we will use any vector to store the path. If we encounter him in obstacle or we can't move further, we just return an empty two-dimensional vector as we did yesterday for appending of the world.
Right. So you will just have a contribution. Basically, you will have a contribution matrix, right?
Yes.
Yes, I guess you all can do this, right? So when you are doing this question, just think about the think about the pruning cases. Think about which are pruning cases. Think about which are base cases. Think about how you are formulating your sub problem. So tell me this: if in this question, if you land up in any cell marked as 0 -1, you will not head down that path, correct? So is that pruning? Do you understand the question? So when you are at a particular cell, you will either, when you go to a -1, you will stop, right? And you will not go further below. So is that pruning or is that a base case or is that something else? Depends on, that's what. So it depends on how you formulate the problem. If you are formulating your problem as if your problem is you have to enumerate all paths avoiding the -1s, then that is not a part of the problem space, right? Right, Karan, Pranav, Divya, do you understand what? And if your problem statement is that you are enumerating all possible paths and then taking only those paths which are valid, and by valid you define valid as covering all the cells and not going over -1s. If that is how you define a valid, then yes, it is pruning. Do you see what I'm trying to say here? Akshay and Drishan also? Yeah, so it depends on how you are formulating the problem. Depends on the recursion tree. If it is not a part of the recursion tree, then it's not everything in the subproblem space will come in the tree. And everything to the which is outside or not a part of it is basically your not a valid subproblem.
So
Yeah.
So like, for example, in that other problem where you find the word, in that, for example, if you take the word offer and there's a two-dimensional matrix and you put the words offer in it, there are basically two ways you can go and find the word offer, right? So this is basically, you're just counting the number of times you can find the word.
In the question, we just had to return a true if we found it even once.
Yeah, but if we had a question where you have to count the number of ways you can find the word, it would be two, right? In the case of offer, because it's a palindrome. It's almost similar to this question, right?
Yeah. I mean, if in that case, yes. So all unique paths would count as different answers.
Yeah,
So
okay.
that is a unique path. This is also a unique path, different path, right?
Okay.
So yeah, it will be two. So you will be able to code this on your own? Yeah, all good?
So,
yeah.
So if we define our problem as finding all possible paths, regardless of if we're going over a 0 or a -1, if we did it like that, then we would treat like encountering a -1 as a case where you would then go back to the previous state. So then it would be a pruning step. Like
Yeah.
if you, okay.
Yeah, you're right.
Okay.
Pruning is basically you are not enumerating some of the possibilities because you know beforehand that those possibilities will not help you. They are not valid or good as we were defining them. That's basically pruning. So how you define the problem statement, your possibilities space, the space of all the possibilities is dependent on how you define the problem statement. Here, if you define the problem statement as that I don't want to go over the -1s at all, then your good and bad possibilities are good possibilities are ones where you reach the end visiting everything once. Bad possibilities are either you don't reach the end, or even if you reach the end, let's say you have not visited every cell once, you are still following the constraint that you will be avoiding -1s, right? So still you have good and bad possibilities depending on how you formulate your sub problem. In both the cases you have your good and bad cases.
Okay, so and in the previous problem, we had not used the contribute, like giving your contribution to the
Yeah, because it was typically, so if you are typically interested in just returning either whether it's possible or not, there is no contribution that you need to pass. In this case now, here you will have to pass down the contribution. You pass down the contribution of this particular cell in the path. So when you reach the end, you will be constructing a path, right? You would have constructed a path. So you would want to push that path to the result if that path is a valid path, right? So one way of doing it is that you could construct the path after you come back. And the other way is you could pass on your contribution into the path. And at the base case, you would push that path in the answer.
So, but here we have to return only the number of the paths, right?
Return the number of 4-dimensional works. Yeah, then it's good. I mean, you can, here you can, yeah, I mean, then it's fine. I don't think you will have to. You can get away without any contribution.
Okay.
Yeah. But if they told you to enumerate all the paths, then you would have to pass down the contribution. Okay, you guys are confident you will be able to do it, right? It's not very hard. In fact, it's more easy or easier compared to the previous question.
More doubt I have.
Yeah.
How can we identify the current path is not the path we have already followed, I mean, we have already taken? Like we have found a path and we are trying to find a different path right now. So there's a chances that we may
no, you will never encounter the same path again, right? Because every time you are going in the 4 directions. So every time you are bifurcating your path by 4.
Yeah.
So it will not happen that you will have 2 paths of the same type. right?
Yep. I got it.
Yeah, any more questions with respect to this? So go ahead, go back home, think about, I mean, you're already at home. Think about base cases, think about pruning, think about backtracking. The formulation still remains the same. It's the same formulation. Recursion, the template that we gave, that the steps, the decision, the reference, everything remains the same. Even for any solution you want to do through recursion, that is the template. So if you want to do backtracking using recursion, that is the template. If you want to do something else through recursion, that is the template that you have to follow. It's just that in backtracking, you can optimize backtracking by pruning. So that's just one additional thing that we did. Okay. So yeah.
So what if the number 2 is in the center? So whenever it encounters 2, should we like skip it and make sure it and like goes through all the zeros and then come back to 2?
No. It's like 2 you can only visit once when you, so it's not a walk, it's a path. I think it's not properly written. Every cell needs to be visited exactly once, right? So you cannot skip for the 2 and then come back to 2. I mean, you cannot keep it a part of your path and then come back to 2, right?
No, but we have to attend all the zeros also.
Yes. Okay.
So if we encounter 2 in the middle, we have to skip 2 and then make sure we go through all the zeros and then go to 2, right?
Yeah, I mean, that path is basically you can truncate that path then and there itself, right? Other paths will take care of that case that you're talking about. You have 4 possibilities from, let's say you are coming from the top, and as soon as you go down, you encounter a 2. So that path now is done. But the other 3 paths from the top, where you could go right or top or left, are still there.
Okay.
Right? Did I answer your question? So they will take care of that thing that you're talking about.
So there'll be part of the part that you have to go to 2.
Yeah, I mean that the decision will take care of that.
Okay.
Every path you are enumerating, you are just terminating that path because you know that it's not possible from there.
Okay.
That would be a bad case if you encounter 2 before visiting the rest. Yeah, I mean, it will be a bad case, yes. If your problem is formulated in such a way that you are avoiding only the minus ones. Okay, so now that is basically, we have 2 more lectures on backtracking. So we will come back and do backtracking, but I have kept a gap between now and those lectures because it's like, I understand 4 consecutive days of this kind of a topic. You definitely need some break to think over it and get it like settled in your brains before we start talking about it again, maybe a week from now. Okay, so we will do more questions on backtracking in those 2 lectures and we will make things more clear. Just one more thing. So if you see, I will just introduce DP. So if you see in whatever all the recursive formulations that we've been doing, what we are doing is we have a problem and we are breaking down it into sub problems. We are solving for all possible sub problems of the problem, and we are then basically using these solutions to solve the actual problem. Right? This is what we've been doing so far. Like all the kinds of questions that we have looked at, this is how we've been doing it. So now consider a case when you had a sub problem SI which you already solved. Now at a later point in your time, in your solution, you need to solve SI again. So there are two ways you could proceed from here. You could either stop here and use the solution of SI that you had found before, or you could solve it again. Correct? So not solving it again and using a solution of a previously solved sub problem is what is dynamic programming. So what we are saying is that all possible sub problems, what we will do is we will store them in a DP table, in any table, so that anytime we are referencing the same sub problem again, instead of solving it again, I will simply look up its value from the table. And that way I will be able to optimize my solution. This is what is dynamic programming. So in all the lectures of dynamic programming that we would be covering, we would typically be looking at ways of storing these sub problems and how, in what order you can compute the sub problems to arrive at a solution to the actual problem. Okay. Do you understand this? I guess most of you already must be knowing this. But now that we have formally talked about problems and subproblems, in like we've been talking about it from the past 4 days, so it's a good segue to DP now. Do you understand this? What I try to say here? Yeah. So this is what is DP. Nothing else. It's not like anything fancier than this. We have already seen ways of how to enumerate all sub problems. We will just, in DP, we will just extend this to store them, so that when we look them up, we can simply look them up from the storage instead of recomputing it again. Okay. Try this problem also. This is a tough problem. It will, but don't get stuck to it. If you're not able to do it, happily move on. It's okay. It's quite tough. It's not that easy. Try this also. So try these problems. These are all from the land of recursion and backtracking. What time is it? It's 11:30. Yeah, I guess we are like almost done. Try these two problems. These are from the decisions of previous classes. Subsets and subsets too. Try these first and then this. All right. So I guess I will see you guys again in some time from now. You can keep practicing recursion. We will have a DPP on recursion soon, maybe today itself, and you can practice them. We will have a doubt solving session for that over the weekend probably, and we can discuss solutions to those questions.
Sir?
Yeah.
सर जो वर्ड सर्च वाली प्रॉब्लम थी उसके अंदर हम डिसीजन मेकिंग में
आपकी आवाज बहुत धीमी हो गई है.
जो वर्ड सर्च वाली प्रॉब्लम थी उसके अंदर कंडीशन लगा सकते थे डिसीजन मेकिंग पार्ट में जो आपने प्रूनिंग करी है, मतलब इफ अगर मतलब वो इंडेक्स से मैच ही नहीं कर रहा, मैं उस पर बैक ट्रैकिंग लगाऊंगा ही नहीं, मतलब बात सेम हो जाएगी।
आप क्या बोल रहे हो कि मैं अगर वो पर्टिकुलर सेल का वैल्यू अगर
मैच नहीं कर रही,
करंट कैरेक्टर से मैच नहीं कर रही है,
हाँ हाँ, मैं बैक ट्रैकिंग लगाऊंगा ही नहीं, मतलब रिकर्जन बैक ट्रैकिंग लगाऊंगा ही नहीं।
वही तो हम कर रहे हैं ना, वो इसको ही तो प्रूनिंग बोल रहे थे।
अच्छा,
Word search, you're talking about the word search problem, right?
yes sir.
So that was the example for pruning that I used for explaining.
ठीक सर।
Okay. All good. All right. So practice these questions, and I will see you guys in some days from now. I don't know how many days, maybe. And yeah, I mean, others, you can leave the meeting. I guess officially we are done. So thank you. Good night. Take care. Bye. And as usual, I'm staying back for a couple of minutes to answer any queries if you guys have anything. Yeah, others can leave. Thank you. Good night. And see you soon. Yeah, Karan, what is the doubt? I had a basic doubt. Is array.size Karan, can you unmute and ask?
Sir,
Yeah.
in C we have to divide by array 0 size to get the number of elements.
नहीं, इसमें array.size से number of elements मिल जाएगा आपको।
ये
वो इंटीजर से मल्टीप्लाई नहीं होता है, मतलब साइज ऑफ इंटीजर से नहीं होगा। अगर आपका एरे 10 एलिमेंट्स का है, कोई भी डेटा टाइप हो, तो एरे डॉट साइज आपका 10 रिटर्न करेगा, 40 या 80 रिटर्न नहीं करेगा।
ये C++ के लिए है या लीड कोड में है सर?
C++ के लिए ये STL है, स्टैंडर्ड टेम्पलेट लाइब्रेरी है, जो कि एक वेक्टर को डिफाइन करता है। लाइब्रेरी है ये।
अच्छा, वो अलग वेक्टर की लाइब्रेरी है कुछ ऐसा?
C++ की लाइब्रेरी है वो, जो कि बाय डिफॉल्ट आती है C++ के कंपाइलर के साथ।
ओके।
जो लीड कोड पे आपने जो अभी कोड सबमिट करा, वो हम देख सकते हैं क्या? मतलब
हाँ हाँ, आपको क्रेडेंशियल्स दिए हुए हैं ना
सर? वो मैंने मिस कर दिया सर एक बार स्लैक पे।
अरे मैं तुरंत लिख देता हूँ, एक सेकंड रुक जाओ। Yeah, I'm just writing the credentials. आप लॉगिन करके, एक्चुअली वो बहुत पहले शेयर कर चुके हैं लोग, बट ऑलरेडी पीपल आर सीइंग सॉल्यूशंस बाय लॉगिंग इन। वो लोग सबमिट भी करते हैं यहाँ पर, बट आप सबमिट मत करना, मतलब इट्स डिस्करेज। ठीक है, एनी मोर क्वेश्चंस?
Sir, could you explain again the problem I am asking about?
The problem?
The matrix.
Come again?
That m dot size वाले।
हाँ, what is the doubt? आपका क्वेश्चन क्या है उसमें, आप बताओ।
सर, आपने m इक्वल टू
हाँ, ये साइज, ये मेरे को साइज देता है बस। ए ऑफ साइज, ए डॉट साइज, देखो आप ए को एक वेक्टर की तरह ट्रीट करो जिसके अंदर छोटे छोटे 1D वेक्टर्स हैं, ठीक है? तो ए डॉट साइज आप करोगे तो वो क्या रिटर्न करेगा? वो रिटर्न करेगा कि कितने 1D वेक्टर्स हैं। तो कितने 1D वेक्टर्स है, एक 1D वेक्टर को एक रो मानते हैं हम लोग, तो कितने 1D वेक्टर है उससे बेसिकली टोटल नंबर ऑफ रोज पता चल जाएंगे। और आप किसी भी 1D वेक्टर को उठा लो, आप A0 डॉट साइज किए ना, आप A1 डॉट साइज भी करोगे तो भी वो आपको M ही देगा।
ओके, अपन n को क्यों नहीं कर रहे हैं?
n को भी कर सकते हो, A of n-1 डॉट साइज भी कर सकते हो, ये भी ठीक है।
n वाले को है ना, जैसे इंडेक्स में 1 लिखे m को यहाँ पर, तो n वाले को कुछ नहीं लिखा है ना, तो इसलिए पूछ रहा था वो वाले।
अच्छा, अब आपको समझ आ गया?
नहीं सर।
बताओ क्या नहीं समझ आया, मतलब क्वेश्चन बताओ।
लाइक यहाँ पर a ऑफ इंडेक्स में 1 डाल के डॉट साइज इक्वल टू m लिखा, लेकिन जैसे कोड में यहाँ 1 की जगह 0 लिखा था, और n जब n इक्वल टू a ऑफ सम इंडेक्स कुछ नहीं लिखा, बस n इक्वल टू a डॉट साइज लिखा है। हाँ वही n वाली जब है तब इंडेक्स क्यों नहीं लिखा बोलते?
तब इंडेक्स क्यों नहीं लिखा?
हाँ,
क्योंकि a जो है वो आपका a भी एक वेक्टर है, a is also a vector, a of 0 is also a vector, a of 1 is also a vector, है ना?
ओके सर।
a is a vector, a is a big vector, a is a vector which has small 1D vectors। किसी भी वेक्टर पे डॉट साइज आप लगा सकते हो, रूल यही है। किसी भी वेक्टर पे डॉट साइज लगाओगे तो वो बेसिकली एक वेक्टर का ऐसा फोटो बना सकते हो ना, ये वेक्टर है। किसी भी वेक्टर पे डॉट साइज लगाओगे तो वो जितने एलिमेंट्स हैं उस वेक्टर में उसका काउंट देगा आपको, ठीक है? तो ए भी एक वेक्टर है, एक ए इस टाइप का वेक्टर है, एक वेक्टर है जिसके अंदर वन डायमेंशनल वेक्टर्स हैं बहुत सारे। तो ए का हर एक एलिमेंट इज अ वेक्टर। हम लोग अभी तक वेक्टर्स ऐसे ले रहे थे जिसमें एक एलिमेंट एक इंटीजर होता था, यहां पर आपका हर एक एलिमेंट ए का एक वेक्टर है, ठीक है? तो जब आप ए डॉट साइज करोगे तो वो बेसिकली आपको रिटर्न करेगा कि कितने वेक्टर्स हैं। तो 1 2 3 4, तो वो 4 रिटर्न किया, जिसका मतलब ये हुआ कि आपके 4 रोज हैं उस मैट्रिक्स में। इस मैट्रिक्स का फोटो हम लोग जनरली रो मेजर फॉर्म में बनाते हैं। तो रो मेजर फॉर्म में क्या होता है कि every 1D vector is one row and not one column। तो आपने जब a डॉट साइज किया तो आपको नंबर ऑफ 1D वेक्टर्स मिले। नंबर ऑफ 1D वेक्टर्स मतलब अगर आप हर एक वेक्टर को वन ऑन टॉप ऑफ द अदर स्टैक अप कर रहे हो तो आपको वो नंबर ऑफ रोज दे दिया। अब नंबर ऑफ कॉलम्स कैसे निकालोगे आप? नंबर ऑफ कॉलम्स मतलब कोई भी एक 1D वेक्टर ले लो, इनमें से सबका साइज सेम होगा, उसका साइज निकाल लो, वो आपका नंबर ऑफ कॉलम्स होगा। तो मैंने फर्स्ट वाले को ले उठा के उसका साइज निकाला था, आप सेकंड वाले को निकाल लो। बट बस अगर आप सेकंड वाला यूज कर रहे हो, ए ऑफ 1 डॉट साइज यूज कर रहे हो, तो यू विल हैव टू टेक केयर ऑफ द केस कि ऐसा भी एक 2D वेक्टर हो सकता है, एक सिंगल रो वाला, तो उस केस में ये सेट फॉल्ट दे देगा आपको।
तो n वाले को अपन a ऑफ 1 डॉट साइज भी लिख सकते हैं ना यहाँ पर, मतलब जैसे?
नहीं, n को आप बोल रहे a ऑफ 1 डॉट साइज?
हाँ।
नहीं, कैसे लिखोगे बताओ? a ऑफ 1 मतलब क्या हुआ? ये a ऑफ 0 है, ये a ऑफ 1 है, ये a ऑफ 2 है ना? a ये पूरा वेक्टर है। a ऑफ 0 मतलब पहला एलिमेंट, पहला एलिमेंट खुद एक वेक्टर है। a ऑफ 1 मतलब दूसरा एलिमेंट, दूसरा एलिमेंट खुद एक वेक्टर है। तो a ऑफ 1 डॉट साइज आप करोगे तो इस वेक्टर का साइज मिलेगा, इस वेक्टर का साइज आपको नंबर ऑफ रोज थोड़ी देगा। इस वेक्टर का साइज तो आपको ये विड्थ देगा, ये जो विड्थ है, ये विड्थ क्या है? ये विड्थ नंबर ऑफ कॉलम्स है।
ओके ओके, वो पूरा साइज देगा।
हाँ, इसका साइज देगा वो। एक बार आप सोच के देखना
हाँ।
अभी, थोड़ा सा स्विच ऑफ करना फिर
मतलब n
वापस।
वाली इक्वल टू a डॉट साइज वाली पूरी मैट्रिक्स का वो जो पूरी साइज देगा ना रोज की।
हाँ
मतलब वही बोल रहा हूँ।
हाँ
सो
यार राधिका।
सर मेरा डाउट मतलब सबमिशन से रिलेटेड है। लाइक सर क्या हो रहा है, हम जैसे लीड कोड में कोई कोड सबमिट करते हैं तो वो मेरा बेसिक टेस्ट केसेस पार कर लेता है, बट लाइक जब सबमिट करते हैं तब मोस्ट ऑफ द केसेस में टाइम लिमिट एक्सीडेड दिखा देता है।
तो ऑप्टिमाइज नहीं है वो।
सर लाइक
मतलब
अभी आपने जो वर्ड ब्रेक
व्हाट्सएप
आपने
वाला
जो
ना।
वर्ड ब्रेक वाला क्वेश्चन कराया,
हाँ हाँ
हाँ, तो मैंने भी उसको किया और मतलब ऑलमोस्ट उसी तरीके से किया, बट फिर भी मतलब वो टीएलई दिखा रहा है और मतलब काफी बड़े वाले केस में फंस जा रहा है। तो
मेरे को कोड भेजना
मतलब
आप, मैं देखूंगा। मतलब वो केस बाय केस बेसिस पे ही समझना पड़ेगा वो, कि वो कुछ ना कुछ मिस कर रहे हो आप, कुछ मिस करते हो जनरली तो ही होता है वो। किसी केस के लिए वो इनफाइनाइट लूप में चला गया है फिर वो, जिसकी वजह से वो टीएलई दिखा रहा है। मतलब आपने फिर जनरली वही होता है कि आपने कोई केस ऐसा मिस कर दिया है जहाँ पर आपका रुक नहीं रहा है वो स्टैक ओवरफ्लो हो जा रहा है, मतलब फंक्शन कॉल करते जा रहा है, करता जा रहा है, रुक ही नहीं रहा, वो इनफाइनाइट लूप में। अगर आपका सोल्यूशन सेम है, मतलब एल्गोरिदम अगर सेम है तो फिर वही केस हो सकता है। तो द बेस्ट वे टू डू इट इज, व्हाट यू कुड डू इज यू could start a thread on Slack in the general channel and you could tag me. I will take a look.
okay, yes, definitely.
Yeah,
Thank you.
no problem. Rahul, you want to prepare for ICPC? I can get you connected with people who have done that. They would be able to answer this question better than me. ठीक है? Of course, I can answer, but I have not participated. Very frankly, I never. It was like I was never interested in it when I was in college. So I can connect you with. You can just ping me on WhatsApp. I can connect you with someone who has done that. I know a lot of people who have even gone to the finals. So you can talk to him or her and get some idea as to their journey and how they went about preparing for it. ठीक है? या मतलब मैं कुछ कुछ बोल दूंगा बट कोई पॉइंट नहीं है किसी और। अब एक्चुअली जिसने करा है उससे पूछना, वो बेटर हुआ। ओके, एनी मोर क्वेश्चंस? टू डिस्कस। ओके, ऑल राइट गाइज, देन थैंक यू, गुड नाइट, सी यू।